Okay, so this will be part two of the enzyme lecture. Sorry about breaking it into two parts. I wanted to get it done for you guys this weekend, and yeah, my dog has a dog buddy here this weekend, and the rescue parrot has her parrot buddy here. So yeah, I'm living in the wild kingdom this weekend. Anyway, but I wanted to get it done just in case you guys needed it. So please excuse my wild kingdom. Okay, so one of the most important things about enzymes is the fact that we can activate or inhibit them. We can turn them on or off. So that's how they have this valve effect of sending molecules to the reactions, the processes, the things that we need, make us what we need to make in our cells, not make us more of things that we don't need or things that we already have. So our glucose example was an example of that, turning enzymes on and off to make energy, to store, or whatever, depending on what we need in the cells. So in Micheli-Menten kinetics, we can do this in a couple of ways. So we can inhibit an enzyme either competitively, competitive inhibition, or non-competitively. And it is kind of exactly what it sounds like. It's pretty intuitive. So we had the enzyme, and we have that binding site that the substrate would like to occupy. So the substrate would like to occupy this binding site. However, if my inhibitor gets in it instead, so let's say the substrate doesn't get to go in there. Oops, I lost my enzyme. The substrate stuck out here because an inhibitor took that binding site. So the substrate stuck out here, the inhibitor took the binding site. That's how we inhibit in a competitive manner. Or in a non-competitive manner, I still have my enzyme. So I still have my enzyme. I have my binding site and I let my substrate bind to it. It's all good. It's there. It bound to it. But I can have an inhibitor bind somewhere else on the enzyme and still inhibit. So that's my non-competitive manner or non-competitive inhibition. The substrate has its binding site. When we're talking about competitive inhibition, the inhibitor will bind non-covalently. Non-covalent sounds kind of reversible, and it is. When I have a non-competitive inhibitor, it's going to bind covalently. Covalent sounds kind of irreversible because it is. So I'll hear you guys doing all kinds of things like don't put your nons together, don't put your C's together, stuff like that. I'll also hear you calling irreversible non-reversible, and then you'll write it out so you kind of go from non to non to non or something. Anyway, you have all your systems for doing that. And I'm encouraging you to do that, use them, because of course this is a really good place to ask you questions. Okay, so a little bit better graphic of the competitive versus the non-competitive. So with the non-competitive, the substrate does get to have its binding site. The non-competitive inhibitor binds somewhere else and can still have the same effect, the effect being the inhibition. Okay, so in competitive inhibition, the inhibitor binds reversibly, non-covalently, to the same site that the substrate would like to have. If I want to get to Vmax, I need a lot more substrate to get there. So let's look at this one. Let's do a biochem story for this. So let's say I usually pick somebody in the front row for this one. Let's say whoever I pick in the front row, that person is sitting there taking really good notes. So they're sitting in their chair. We're going to call their chair the binding site. Then their reaction is taking notes, and they're the substrate. So they're the substrate carrying on their reaction, taking notes in their binding site, their chair. So we have the classroom right now up over the cafeteria, and they heard the waffle guy or the omelet guy was down there. They decided they were tired taking all these really good biochem notes. So they were going to get up and go grab an omelet. So the substrate gave up the binding site, went to get an omelet, and I'm going to be the inhibitor. So I'll be the inhibitor, and I jumped in their seat. So I jumped in their seat, and they left their Facebook open. So that's kind of cool. So I start updating their status. I'm saying I love biochem. Biochem is my favorite subject, all this stuff. And I'm posting the same thing on their Instagram. And I'm just busy as can be going to town doing all this stuff. So don't forget what the reaction is. The reaction is taking really good biochemistry notes. I'm doing all this other stuff. So what did the reaction velocity do in this case? The reaction velocity went down. It went to nothing. I'm not taking notes. I'm doing other stuff. So I shut down the reaction as the inhibitor, taking their chair, taking the binding site. So there's competitive inhibition happening. So now we're going to change the story a little bit. So now the story is this. I'm still the inhibitor. Whoever's sitting on the end of the front row is still the substrate. Their chair is their binding site, and their reaction is taking really good biochem notes. Well, they still heard the omelet guy was there, so they got up and headed downstairs to grab an omelet. So I'm still going to go for that seat, but I have a class of 101 right now while I'm recording the lecture. 101 of you guys, well, I guess 100 of you guys go for that seat also. So now, what are my odds of getting the seat? I'm pretty confident. I think I got it. You guys think otherwise. So having all of you guys as substrate, as in increasing the substrate concentration, that's going to overwhelm the effect of the competitive inhibitor, because now I have a 1 in 100 chance of getting that chair, where before it was just me. I had it. So now if I increase the Km, of course, the substrate concentration that gets me to half of Vmax, more substrate, I'm going to get to Vmax. So for competitive inhibition, if I want to overwhelm it, I'm going to increase Km, or increase my substrate concentration. Okay, so now for non-competitive, we'll tell another biochem story. So our biochem story will be really similar, but this time I'm going to pick somebody who has an empty chair beside them. So whoever is in their chair is still going to be my substrate. Their chair is their binding site. They have their binding site. Their reaction is taking really good biochemistry notes. I'm still going to be the inhibitor. So here's what I'm going to do as the inhibitor. So I'm going to be the inhibitor, and I'm going to sit in that empty chair next to them. So I'm going to pull up an empty chair. I'm going to cuddle right up to them. I'm cuddled right up to them. And every time they go to write, type, or anything, I'm going to elbow them. So they're going to get my little pointy elbow woof, right in the ribs, right in the arm, every time they go to write. For good measure, I'll throw in a little kick here and there too. So I'm kicking and I'm elbowing and all that. So what's their reaction velocity doing is I'm kicking and elbowing. Their reaction, remember, is to take really good biochemistry notes. I just tanked that reaction, right? I just brought Vmax to 0. So I brought Vmax to 0 by inhibiting their reaction, by kicking and elbowing or whatever. So now let's try our same fix. Let's alter the story so that all of you guys are now also substrates. So I've got my substrates sitting in the binding site, sitting in the chair trying to do the reaction. The other 100 of you are now substrate. Can you help the substrate? that's trying to take his notes or her notes. No. He has or she has her binding site. They're in their binding site. I'm hanging out someplace else, not bothering the binding site, but interfering. So we've decreased Vmax, and there's not a thing we can do about it. Increasing the substrate concentration didn't help. So we're not interfering with the bonding, so Km didn't change, but Vmax absolutely did change. So I'm decreasing Vmax no matter what. Okay, so that was our Michele-Menten. All well and good, but we're not going to use it. Boards like it, so that's why we have to do it. So we're going to talk about allosteric enzymes. So allosteric enzymes are kind of a combination. So what do I mean by that? What I mean by that is they have some similar trends and similar functions. The kinetics are completely different. So in Michele-Menten, we had our substrate concentration, our reaction velocity, and our graph came up and tapered off. That was supposed to be starting at 0 down here. So it came up and tapered off. With allosteric enzymes, the kinetics are different. We can have the graph, substrate concentration, we have our reaction velocity, and we have a sigmoidal dependence of reaction velocity on substrate concentration, as in we have a little bit of a drag first, then come up and level off. So whole different kinetics, different everything, different animal. We have this drag first that makes the curve an S shape. Remember, a sigmoidal curve is an S shape, S for sigmoidal, S shape. Just as an easy way of remembering it. So when we're talking about allosteric enzymes, we have inhibitors and activators, and we call those molecules that activate or inhibit, we call them effectors, need to know that word, or modifiers, need to know that word. So your effector or your modifier is your activator or your inhibitor. Your activator or your inhibitor binds to the enzyme somewhere other than the binding site. So they bind in a non-competitive manner. Well, that sounds like non-competitive binding someplace else other than the binding site. I say it kind of funny like this, saying non-competitive manner rather than just saying outright non-competitive, because I want you to make this distinction that the kinetics are different. Actually, let's talk about that for a second. Most books present this material this way. What they'll do is they'll be talking about enzyme kinetics, and they'll have a category. They'll have Michele-Menten, and they'll say A, competitive, B, non-competitive. Then they'll say allosteric, and I guess we only have an A, the non-competitive. And this is the more common way it's presented. But another way you could do it is you could say non-competitive, A, Michele-Menten, B, allosteric, and then competitive, and just have, say, your A, your Michele-Menten. The second way makes it more clear that the non-competitive is different with the Michele-Menten and the allosteric. Of course, my graph coming up and over, my graph dragging, and then coming up and over. So I'm just taking the second and pointing this out now because I want you to be clear on this difference. And that's why I'm saying it in kind of a goofy way too, saying non-competitive manner. I just don't want you to mix those two things up. Then they also bind non-covalently. I've heard some of you guys who have old black market notes say they're the non-enzyme, and that's fine. They get all the nons, the non-competitive, the non-covalent. I just want you to realize they are really and truly an enzyme. I don't want you to take that non as implying that they're not an enzyme. It's always easier to be the person who wrote the notes when it's time to understand them than try to make sense of somebody else's notes. And of course, non covalent sounds kind of reversible, and it is. So, we're going to look at different types of effectors here. So, we're going to categorize this, and this is going to be our approach is going to be kind of mechanical, kind of like we did with our acidosis and alkalosis. You figured out, is it acidosis or alkalosis? Then you figured out, is it respiratory or metabolic? Um, or like our hypo volume tone, you do one half and do the other half. Okay, we have two types of effectors in terms of whether they activate or inhibit. So we can have a negative or a positive effector or a modifier. Our negative effector inhibits. Our positive effector activates. That's it. So let's go to another page and just break this down. So my effectors or my modifiers, and I'm in my Micheli-Menten. These are AKAs for each other, effector and modifier. I can have a negative effector. It inhibits. Easy. I can have a positive effector. It activates. Easy. So you just look, does it activate or inhibit? Then the other category that I separated in, like remember with alkalosis and acidosis, you had to figure that part out. Then you had to figure out separately your respiratory versus metabolic. I can have a homotropic effector or I can have a heterotropic effector. Homotropic effector is the substrate of that enzyme that we're talking about. Doesn't matter if it's the substrate of another enzyme. The heterotropic effector is anything but the substrate of that enzyme. Okay, so let's look at this. So I have my fakey little reaction or my process. I have A going to B, going to C, going to D. I have enzyme 1, enzyme 2, and enzyme 3. So we'll go through a few examples. I don't remember what examples I did in class, so they'll very likely be different, but that's fine. So positive or negative is simply activate or inhibit. So you have to be told, does it activate or does it inhibit? When you guys are actually using this, when we do it, my questions, of course, will give you activate or inhibit. When you're actually using it, you're going to use it the other way around. You'll be told something has a heterotropic positive effect on whatever, and you're going to back up, say, okay, well, it's positive. That means it activates whatever you tell me about. It's heterotropic. It's not the substrate of whatever you're telling me about. So when you use it, it's going to be backwards from the way we're asking questions, but it's a little tougher to ask you questions the other way around, more in the application sense. Okay, so positive or negative, easy, activates or inhibits. Heterotropic, homotropic, just look and see if it's the substrate of that enzyme. So the only thing that can have a homotropic effect on E1 is A, because A is the substrate of E1. If anything else, B, C, or D, has an effect on E1, it's got to be a heterotropic effect. Or the only thing that could have a homotropic effect on E2 is B, because B is the substrate of E2. If somebody wants to mess with you with questions, they would say A is a substrate of E1, blah, 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 but B affects E2, and ask you about A. Actually, let me back up on that. What they'll do, I don't know if I said that right, I'm sorry. They'll say A is a substrate of E1, but it has an effect on E2. They'll put the word substrate out in front of you to plant the seed. If A is affecting E2, it's not the substrate of E2, so that would still be heterotropic. The only thing that could have a homotropic effect on E2 is B. Same thing, C. The only thing that could have a homotropic effect on E3 is C. If anything else affects those, they're going to be heterotropic. So let's say lots of A activates E3. So this will just be an example. Lots of A activates E3. So you're going to look first at activates. So that's your positive. Then, I'm sorry, I forgot to write the A in. A is activating E3. Well, is A the substrate of E3? No. C is the substrate of E3. A is the substrate of E1. So it's got to be heterotropic. So that's your heterotropic positive. Let's do it another way. Lots of A activates E1. So now what? Activates, that's my positive. Is A the substrate of E1? Yes. So now homotropic. Or another one. Lots of C inhibits. How about E2? So look first. Activates or inhibits? Inhibits. Negative. Is C the substrate of E2? Here's E2. Nope. C is actually the product of E2. C is the product of E2, but the substrate of E3. So it's not the substrate. So we're heterotropic. So dig through it that way, because your answers, your offers, of course, will be heterotropic positive, heterotropic negative, homotropic positive, homotropic negative. So go through like that, very mechanically, like we just did, and you'll be fine. The other thing, and we didn't do this in class, I'll try to remember to do it. The other thing is, if you need to, when you're given a real reaction, put A and B in there, go ahead and do that. Let's do something else quick first. If I have something like A and B goes to C plus D, and I have my enzyme, don't forget that A and B are both substrates of E1. So if either A or B were to be the effector on E1, that's still homotropic. Anything else is still heterotropic. So it doesn't matter how many substrates I have, if one of them is the effector, it's going to be homotropic. Okay, so let's do something else. This is just kind of how to do it. Let's say I give you the reaction. Glucose goes to glucose 6-phosphate. This is a reaction we'll do. And hexokinase is the enzyme that catalyzes that reaction. What I'm going to tell you is this. Lots of glucose 6-phosphate inhibits hexokinase. So when you look at that, you're thinking, well, hold on here. What's going on? What's what here? Here's what I would do. I like A goes to B with E1. That's what I'm used to seeing. That's what I practiced with when I was studying and everything. I'd go A, I'd go B, I'd go E1, B, E1. So now it turns into what we just had. Lots of B inhibits E1. So what is it? Inhibits, negative. Lots of B, is it the substrate? Nope. A is, B is the product. So heterotropic. So don't be afraid to use your scrap paper. Turn it into a form that you're used to seeing. Okay, I think that's it for enzymes. Yeah, that's it for enzymes. Okay, I'll try to get the next PowerPoint recorded for you guys this weekend. If not, I'll do it after class on Monday. Hope you're having a great weekend.